Welcome to the lecture on preheat and post-weld heat treatment of weldments. So, we discussed about the different welding processes, and we also have seen that how there is chances of the formation of residual stresses, and then there are the possibilities of deformation, distortion in the weldments. So, one of the very important process which are implied in most of the cases to avoid this distortion or to relieve the weldment of the residual stresses, the preheat and post-weld heat treatment of weldments, they play an important role. So, this is preheating we are talking about, or post-weld heat treatment. They are required for successful welding of materials of high thermal conductivity of thick sections or hardenable materials. So, basically the challenge comes when we have these materials of suppose high thermal conductivity. Now, in those cases the heat transfer from the weld specimen goes very fast. So, if even if you are having in normal cases when you are using the heat source, and if the conductivity of the plates is quite high, in those cases it is very difficult to contain the heat at that point and do the proper fusion of the material. So, in the case of that you have the challenge. Similarly, in the case of thicker sections and also among the hardenable materials where there is quite a big chance of formation of martensite phase, which is normally brittle. So, there also that is the challenge, because even in the normal cooling rate you have the chances of formation of martensite, which is undesirable, or martensite may be formed which is completely brittle. So, which is undesirable. In those cases you try to slow down the cooling rate even than the normal. So, that way you will have to have the special type of treatment given, so that that leads to formation of the phases which are not so undesirable. When welding is carried at low temperatures, cooling rates are usually high. Now, again another situation may come when we are welding at lower temperature below 0 degree centigrade. So, in those cases what happens that once you do the welding, and as the ambient condition is at very low temperature, ambient temperature is quite low. So, the cooling rate itself which is developed is quite high, and when the cooling rate is quite high, in those cases because of the stresses generated, there may be formation of cracks in the welds. So, when we are doing the welding under those conditions of lower temperature, again there is a challenge, and in those cases you need to have this special provision of the pre or post weld heat treatment, so that you get the satisfactory results. This is primarily about the preheating, and then we talk about the post weld heat treatment. Now, in the case of post weld heat treatment, the primary aim is for the stress relief treatment. So, what happens in many cases, the stresses generated are quite high. So, for relieving the weldment of the stresses, we do this post weld heat treatment, and in that case normally what we do is we are heating to a temperature of somewhat higher degree than that is required in the case of preheating, and then there we are holding for some time and then cooling. So, that is required so that the stresses are relieved, and this is necessitated. The need is that much felt only because if you are not paying the proper attention on this preheat or post weld heat treatment, then undesirable phases may occur. There may be brittle phases, there may be cases where there may be stress corrosion or so. So, in those cases if the brittle phases are present or brittleness occurs, then there is a chance that there is catastrophic failure of the welded component. So, that is the challenge with these preheat and post weld heat treatment processes, that's their importance lies behind these concepts. Now, what are the aims of preheating? So, as we discussed that the aim of preheating is to reduce the heat loss from the weld area, to reduce the cracking by preventing the formation of hard surfaces or hard faces, many a times hard faces like martensite or so, to reduce the expansion and contraction rates. So, in many cases what we see is that if the expansion coefficient is coefficient of linear expansion is larger, in those cases the chances of deformation is more and the stresses generated, and that may lead to deformation. So, in those cases if you are doing the preheating, in that case the rate of heat transfer will be smaller and the expansion. So, expansion basically will be depending upon the change in the temperature. So, if your temperature is a small temperature difference basically. So, if the temperature difference is smaller, in that case expansion will be smaller or contraction will be smaller. So, that way it helps in reducing that. Then it is also important aim is to burn the grease, oil or scale from the joint area. So, many a times when you are going for welding, then the specimen which is to be welded, which was kept priorly, so that may have the grease, oil or scale, or sometimes may be painted, or maybe you have some other substances which are actually volatile. So, if you preheat, then they are basically gone. So, they will be going off of the surface, otherwise they are going to create the problems in the joint. There may be inclusion of the impurities and other type of defects if they remain on the surface. Bring the temperature above and avoids brittle fracture. Many a times when the temperature goes quite low and we do some thermal treatment, in that case there are some brittle phase formation. So, in this case if you are having that temperature, then the temperature difference not being that much, the chances of the brittle phase formation is less, and so the brittle fracture chances become less. To help allow sufficient time for hydrogen to diffuse out of weld and HA jet. So, if you are preheating, then that way you are allowing the hydrogen to come out and you are giving the proper time. So, hydrogen induced defects, its chances become less. So, these are the aims of basically preheating. Now, method of preheating. So, when we talk about the method of preheating, how we can do preheating, like you may do with the flame. So, you can use the oxy fuel gas heating torches. So, you have torches of diameter, then you have from there you can with the supply of the gas you can generate a flame of different type, like maybe we know that we have 3 types of flames. So, then with that flame you can do the preheating, like oxidizing or reducing or neutral type of flame may be generated, and then you can do the preheating. So, the attributes of such flame heating with oxy fuel gas heating are like they are low cost and portable. So, that is the advantage of that type of flame heating mechanism, because you can take them to any place. You need the cylinders of oxygen and acetylene, and you can generate the flame and you can heat it. But then the disadvantages are like you have minimum of the precision and repeatability, because they are done normally manually. So, precision is also because, and also the flame has spread. So, the precision is also less. Then you have a non-uniform temperature distribution also. So, that is the disadvantage. Then you have electrical resistance heating. You have the resistance coils which are there, and because of the electrical resistance mechanism you do the heating, and its advantages are that they are continuous and even heat maintained throughout the welding operation. So, you can be assured that there is even heat which is maintained throughout the welding operation. temperature can be adjusted quickly and accurately. So, that is further an advantage. And many a times we see that there are also disadvantages, like uneven heat also can be obtained in these cases. So, then you have the induction heating. Induction heating is further the another mechanism by which you can do the heating. So, it has the advantage of like you have high heating rates, and also temperature is controlled within the narrow range. So, this way you can maintain that, but the disadvantage is that you have high initial cost, and also the equipment is bulky. So, that is the disadvantage. Then you have the quartz lamp heating, which has the advantages of fast response time, efficiency, cleanliness, fast cooling down. These are the advantages, whereas the disadvantages are like you have high initial cost, fragile and sensitive to contamination. So, this way you have the different type of heating mechanism, and you can do the heating, and depending upon the situation where you are welding, or depending upon the case to case, you can use the different any kind of heating mechanism and do the preheating. Now, we will discuss about the preheat temperature of different materials. So, among the materials we have, suppose we discuss about the carbon steel. So, in the case of carbon steel, the preheating is necessary for the heavy sections, because when the carbon content is smaller, then you do not require that much of preheating. But so, when you have a carbon content to lower side, then you do not require the preheating, because the hardenability is less. In that case, hardenability increases with the carbon content. So, if the carbon content becomes larger, in those cases you have the more chance of formation of martensitic phases, and in those cases there will be chances of having the more stresses and all that. But as the carbon content increases, or even the alloying elements increase, so that also have the effect on hardenability that we will see, and in those cases you need the preheating. So, preheating basically when you have less than 0.2% of carbon, then you do not need that much of preheating requirements. But when the preheating is more than 27% or 25%, in those cases you need the preheating, that becomes necessary. Also, preheating becomes necessary for heavy sections, and when you have such heavy sections, in those cases, even if the carbon content is less, in those cases, because you have large heat content into the zones. So, in those cases you need the preheating temperature of about 100 to 200 degree centigrade, and because in the case of heavy sections, the weld pool being basically surrounded by, or being in adjacent to the thicker parent metal on both the sides, the heat extraction rate will be quite faster. In those cases you require the preheating, and preheating temperature which is normally suggested is about 100 to 200 degree centigrade. But it should be also seen that it should be below the critical ductile to brittle transition temperature there, especially if you are doing the welding in the case of winter, so then you have to be careful that the temperature should not be below that. Now, also it is seen that if the material has not the impact value of about 8 to 10 joule, in that case also the considerable danger is there for the cracking under the stresses. So, that value of toughness, so that is required to be having that. Now, in the case of medium carbon steel, as we discussed, that when the carbon component carbon percentage becomes more, in those cases the chances of I mean hard reliability increases, the chances of formation of martensite with ease will be more. So, in those cases you require to have the preheat, and preheat temperature is suggested to be close to I mean in the range of 95 to 370 degrees C. So, depending upon the carbon content, means if the carbon content is more, in those cases you require to have more of the preheat temperature, and if it is less, in that case you can think of having lesser of the preheat temperature. If you talk about the plain high carbon steels, when you talk about the high carbon steel and it is plain, means there is not much of the alloying elements, in those cases as the carbon percentage becomes more, so in that case it will be difficult to weld. So, weldability or difficulty in welding basically increases with the carbon percentage. So, in these cases you require to go for the preheat temperature of about 205 to 370 degrees C if the carbon is more than 0.6, and if it is 0.45 to 0.6, in that case we go from 95 to 205 degrees C. A control system of preheating is maintained for such materials. Now, if we talk about the low alloy steels, now in the case of low alloy steels, most of them are hardenable. So, hardenability is basically measured in terms of CE. CE means when we talk about low alloy steel, you have alloying element which is around 5% or less. Now, in those cases the role of the alloying elements also is towards the hardenability. So, hardenability is not only because of carbon. When we have the plain carbon steel, then in that case you have mainly alloying element is carbon, but then otherwise when we go about the low alloy steels, in those cases what we do is we have to find the value of the carbon equivalent. Depending upon the percentage of alloying elements, we find the value of the carbon equivalent, and this carbon equivalent value is a function of the alloying elements. So, as the alloying elements increase, then the carbon equivalent value increases, and if the carbon equivalent value is more, in that case the preheat requirement will be more and more. So, that way you go for the finding of these preheat temperatures, like many a times what we see that for normal steels you have percentage of carbon plus percentage of manganese by 20, then percentage of nickel by 15. Similarly, chromium, molybdenum or vanadium, their percentage added by 10. So, this way you get like the carbon equivalent value, and then depending upon the carbon equivalent value, if the carbon equivalent value suppose increases more than certain value, in that case you have to go for the preheat. So, it has been seen that if you are suppose dealing with a plain or low alloy steel, and if you have the carbon equivalent above about 0.4, then you go for the preheat of about 50 degree centigrade. Then if you have the 0.45, then it will go to 100. So, like that. So, so that way the carbon equivalent changes, like if you have carbon equivalent and then preheat temperature. So, it will be for 0.4 it will be 50, like it will be 0.45 it will be 100, then it will be 0.5, then it will be 150, then 0.55, so it will be 200, 0.6 it will be 250, and similarly it will be 0.65, in that case 300. So, this way there has been suggestions that you can have the value of the preheat for the plain and low alloy steels. We find first the carbon equivalent depending upon the alloying elements, and then we try to see that how much should be the preheat temperature. So, that way we can have it. Another method which is suggested for this low alloy steel is the susceptibility index. In that method of susceptibility index grouping, we find the susceptibility index value, and this susceptibility index value will be depending upon the composition parameter. So, that is PCM also, or it will be it will be simply a function of the similar to that carbon equivalent. And once we get that value, then basically what we do is we determine the preheat and interpass temperature based on the level of restraint. So, like we find the composition parameter, and again composition parameter is a function of the percentages of the alloying elements. So, percentage of carbon plus you have other alloying elements. So, for silicon, if suppose divided by 30, then for manganese divided by 20, like that. So, you have these values of susceptibility. So, this way you get the composition parameter PCM. So, in those cases we first find the PCM, and then from that you get the, depending upon the hydrogen level, we also get the susceptibility index. So, basically first of all we find the PCM. So, this is composition parameter. Composition parameter is basically a function of the percentage of carbon plus the contribution by the other alloying elements, like you have silicon, manganese, molybdenum, vanadium, all that you have, or you have other elements. So, you have a standard formula. That formula is used to have the composition parameter. So, percentage of carbon plus all that. Once you get the composition parameter, then you get the value of susceptibility index depending upon the hydrogen level in that melt. So, based on that you have the value of susceptibility index, that is 12 times PCM plus log 10 H. So, susceptibility index SI, that is susceptibility index, so that will be 12 times PCM plus log 10 of H. Now, this H is basically the level of hydrogen, and you have levels of hydrogen like H1 or H2 or H3. So, H1 means you have 5 milliliter per 100 gram of weld metal. So, this H has 5 milliliter per gram of weld metal per 100 gram of weld metal, or 10 or 30. So, this H will have the level. So, this is H has 3 levels, and that is H1, H2 and H3. So, in that case, and this level, basically level is nothing but suppose in H1 5 ml per 100 gram of weld metal, then here you have 10 ml per 100 gram, and here you have 30 ml per 100 gram. So, this way once you have that H, and once you know the susceptibility PCM, in that case you have you can find the susceptibility index. Now, after finding the susceptibility index values, you can have you have depending upon that you give the susceptibility index value, and then based on that you define a preheat and interpass temperature for different materials. So, that temperature will be basically maintained for different type of materials, and that is how we say that how can you control these preheat or interpass temperatures, how can you define or set the preheat or interpass temperatures. Now, in that also you have the different type of restraint is there, like you have low, medium and you have the high level of restraint. So, how much freedom you are supplying, how much the structure is having the freedom. Based on that you have the restraint values, and on that also you have the value of preheat that is determined. So, basically normally we define, like when we talk about the low restraint, means it is like about common fillet or groove welded joint, and where the freedom is there for the movement of the member. So, similarly if you have medium restraint, in that case it is attached to a structural network already. So, that way you get it, you give that, and when there is no at all movement, so in those cases you have say that it is the completely high restraint of type of weldment is there, and in those cases the accordingly you will have to define the preheat temperature. Now, we will go to the other kind of steels, like for HSLA, that is high strength low alloy steels. In those cases when you have the thickness of more than 25 mm and you have the high restraint joints, then temperature is about 40 to 200 degrees centigrade is taken. Similarly, for stainless steels you have the preheating necessary for reducing the effect of Martin-Stick transformation. So, that is another requirement in the case of stainless steel, where the preheating of 100 to 300 degrees C is used, and for normally for thickness of less than 10 mm, and when the chromium percentage is about 13% and carbon 0.1 to 0.12%, in that case there is no requirement of preheat in those cases. Preheating is very much important in the case of aluminum alloys also. Aluminum and its alloys, as we have discussed, that in the case of aluminum, or we have discussed in general for other materials which have very good conductivity, or in those cases you have good thermal expansion coefficient. So, in those cases to avoid that or minimize the expansion and formation of cracks, because when you have the more expansion or contraction coefficient, then if you do not do the preheat, then the temperature differential will be high and the chances of expansion or contraction will be more, and with some restraint there can be the distortion or so. So, in those cases when the plate is having thickness of more than 6 mm, then you require preheating to a temperature of about 150 to 260 degrees centigrade. So, that is the requirement in the case of this aluminum. Now, when we talk about the MIG or TIG welding, in those cases we have the concentrated heat source, so that can go, and in that case we do not require the use of basically preheat. So, without preheat also, if you are using the TIG or MIG, then you can do it, but otherwise in normal other arc welding processes you require the preheating. Now, as we discussed that in the case of aluminum, deciding that what is the temperature, so that now preheat actual temperature has reached, for that, because aluminum does not show any change in color, so it is very difficult. So, for that there are certain experienced welders judged by experience. Either you can use the thermocouple, or there are uses of some, like you have the carpenter blue chalk, which will turn white at that temperature of preheat. Similarly, you have pine stick, which will have a mark on left on that specimen, or you may have the use of hammer to stuck, and you will not find the metallic ring in those cases. So, you assume that now the preheat temperature has already been reached. Similar to preheat, your requirement is also for the post weld heat treatment, and normally in the post weld heat treatment what we do is that is required for removing the stresses. So, the annealing is the best way to go for the post weld heat treatment. Now, annealing can be done either for the only the component which is welded of that part of weldment, or for the whole component. Then annealing may also be done like full annealing or subcritical annealing. So, that may be also carried out depending upon the what is the requirement. Then local lowest temperature stress relieving also is carried out. Basically, the purpose is to relieve that from the stresses. So, the local low temperature stress relieving is also carried out. Other methods which are there in the post weld heat treatment is that you have the quench annealing, normalizing, hardening and tempering. Now, in the case of annealing, you will have to have certain precautions, and what we do is normally when we do finish the welding and then we are coming, then in the case of suppose you take the steels, in those cases you are further coming, you do not go to the room temperature, rather you further heat and go to a temperature larger than the mortar stick finish temperature, and for the heat treatable basically low alloy steels, and then there you are holding for some time and then further cooling. Similarly, when we talk about the martensitic steels, in those cases you are cooling down below the MF, then further you are holding there for some time and then further you are heating and going to about 750 degree centigrade, then you are staying there for certain time. So, in normally you have 600 to 700 degree centigrade of preheat temperature is there, and that also is there for different value for different types of steels, and there you have to maintain some time and then you have to cool in a controlled atmosphere so that the stresses are relieved. So, you have the different post weld also heat treatment cycle for different components which can the main thing which is to be kept in mind that they are for the stress relieving purposes. So, that is to be kept in mind. So, that is about the preheat and post weld heat treatment cycles. Thank you very much.